you to check the health, capacity, and performance of your cloud resources. You can then use this data to determine when to launch more instances or handle increased load, troubleshoot issues with your instance, or better understand system behavior. Services like data science, compute databases, and other continuously emit metrics to the monitoring service as active monitoring. Alarms is a passive monitoring service that gets triggered when a metric breaches set alarm threshold. In this example, an alarm triggers a notification when CPU utilization exceeds 80%. At that time, a notification is invoked and a message is sent to all subscribed topics, which are communication channels such as Slack, SMS, or email. Metrics, alarms, and notifications are all integrated services that work together to monitor the status of your service. Metrics track CPU and GPU utilization depending on your instance, the percentage of available job run shape memory, network bytes in and out, and disk utilization. When these numbers reach a certain threshold, you will want to scale up your resources such as block storage and compute shape to accommodate the workload. With jobs, customers can either use service or custom logs. Service logs are standard out-of-the-box logs emitted by the job run to OCI logging service. Both standard out and standard arrow outputs from your job artifact are captured and made available in the service logs if enabled. The job run resource principal must also have proper permissions to write to your service or custom log. With custom logs, the customer captures log events collected in a particular context and specifies the location where the logs will be stored. Enabling the jobs logging service is optional but recommended, both for debugging any potential issues and for monitoring the processes of running your job artifacts. When logging is enabled, you can provide your own log group and log to capture job run outputs. Each job run can send outputs to its own log or all can use the same log. You can enable the data science job service to automatically create service logs on your behalf at the start of each job run within your specified log group. If automatic log creation is enabled, there is no need for you to configure logs yourself before each job run. You manage the lifecycle of the logs, including logs that are automatically created for you by the data science service. Logs aren't deleted when the job and job runs are deleted. The event service lets you subscribe to changes in your resources, like the job and job run events listed here, and it responds to them by using Oracle functions, notifications, or streaming. An event is a structured message that denotes a change in a resource. An event is usually a CRUD operation, which stands for create, read, update, and delete. To interact with the event service, users create and manage rules which allow customers to select the events they want to monitor and trigger an action. An action is a user-defined response to a rule that matches an event. During the lifecycle of a job, events are automatically sent to the event service, where customers can configure an action for each event. Supported actions include triggering either a notification or a function, and a user can specify multiple actions per rule. The event service guarantees at least one delivery for all actions. To wrap up, in this module, we've learned about the monitoring service and the jobs metrics. We've shown the jobs logging options and when to use them, and we introduced the event service and its support in jobs.
Hello and welcome to the new lesson Data Science Pipeline. I am Hemant Kahankari. I am a Senior Principal Training Lead at Oracle University. In this lesson, we will explore what a data science pipeline is, its components, its life cycle, and I will also explain you a setup being used to demonstrate a data science pipeline in a subsequent video. In the earlier lesson on data science jobs, we saw that using a data science job, we can implement a custom task. Using pipelines, we can implement a end-to-end workflow having multiple such tasks. Let us see what data science pipeline is. Pipeline is a new feature of the OCI data science service. It consists of one or typically multiple steps. The steps could be data processing, model training, model evaluation, and model deployment, and so on. Each step is discrete and gives you the flexibility to mix different environments and programming languages. So, for example, if we want to use Python for data processing and we want to use Java for model training, we can do in a single pipeline, and steps can have dependencies on other steps to create a workflow. So some of the steps could be in sequence, executed in sequence, and some of the steps could be executed in parallel. There is a pictorial depiction of a pipeline. We see that pipeline consists of multiple steps. For example, step 1 could be data processing. Step 2A, 2B, and 2C could be model training. Step 3 could be model evaluation, and step N possibly could be a model deployment. The steps can be executed in sequence or they could be executed in parallel. By default, the pipeline tries to execute all the steps in parallel unless we set the dependencies to execute them in sequence or in parallel. The dependencies allow us to create a logical workflow. For example, we might want to do the data processing first and the model training after that and the model evaluation after that and so on. We also have a default configuration associated with a pipeline. So pipeline is a resource that we want to execute. So for that, we define a compute shape. To do the execution, we also need to select the suitable block volume. So environmental variables will allow us to pass certain data, say something like data location before we start executing a pipeline. We also need to define the log settings, maximum runtime for the pipeline. And we have the default settings at the pipeline level, and these default settings will be used when not defined in the pipeline steps. So here is the pictorial depiction of a pipeline step. Pipeline step also has a default configuration. If we set the default configuration for the pipeline step, it will override the default configuration of the pipeline. The pipeline step can be implemented as a script or a job. If we implement it as a script, we can provide a step artifact in the form of a Python, Bash, or a Java file. It could be a single file or it could be multiple files zipped together. If we implement it as a Oracle data science job, we can identify the pre-created job using the OCI. The pipeline step can also access OCI resources like object store and databases provided we set up the right policies to allow the access. We can also use external resources in the pipeline step provided we set up the appropriate VCM. Let's go through the pipeline lifecycle. When we create a pipeline, it goes into a creating state. When the creation of the pipeline is complete, it goes into an active state. And that is when we can start running the pipeline. The pipeline run is an execution instance of a pipeline, and we can have multiple execution runs. And once we are done with the pipeline, we do not need a pipeline. We can go and delete it. In this slide, we will discuss a scenario that has been used to record a demonstration video. So in the step 1, what we will be doing is we will be reading a file from the object store. We will be processing it using the operations like dropping the columns, applying the label encoding, scaling the data, and finally we will split the data into train and test data files, and we will save it to the object store. And to let the step 2 know of the location where we have stored the file, we will also set the pipeline variables. In the step 2, we will train three models using three different algorithms like linear regression, random forest, and XGBoost. We will store the trained models into the model catalog. And in the step number three, we will essentially pull all those models from the model catalog, and we will select the best model and we will deploy the model. So in this lesson, we learned about what a data science pipeline is, its life cycle. We also discussed the setup for the demonstration, and we also understood that it is a very important feature if we want to automate the machine learning or a data science workflow. In this demo, we will see how to create a data science pipeline and run it to automate the complete end-to-end machine learning workflow. The pipeline that we will create and run will have multiple steps, and the code for those steps is available in the Oracle samples GitHub repository. More specifically, we'll be using the OCI Data Science AI samples repository. We can download the code for this repository by clicking the code button and choosing the download zip option. I already downloaded and extracted the code into a local folder. I'll walk you through that local folder. As you can see here, this is the master folder that I have. Within that, I have pipelines folder. Within that, I have samples folder. And we'll be using employee attrition sample in this particular case. Within this particular folder, we have multiple zip files, and those zip files we'll be using to implement the steps that we have in the pipeline. Now let us see how to create a pipeline. For that, we need to create a data science project. I already have created a project, so I'm going to use that. So under the data science project, I have pipelines options here. So under the pipeline, I can use the create pipeline button here. So I get a create pipeline page here. So we can give a name for the pipeline. So let us say employee attrition pipeline. We can provide some description. So we will say for demo for now. We will come back to the pipeline steps a bit later. Let us see the default configuration for the pipeline. So we are going to be providing one environmental variable here, data location. That is going to be a OCI bucket. I already have pre-created this bucket. Pipeline temp bucket. We are not going to be providing any command line arguments, and we will not change the maximum runtime in this case. We will also select the compute shape, a default compute shape for the pipeline. So we are going to be selecting VM standard 2.2. Here we will select the default block size also, so which we are going to be selecting as 50 GB. We will select the log group also. I already have pre-created a log group. I'm going to select in this case. By default, the automatic logs will be created, but otherwise we can select a specific log also. So let's run through the configuration once again. So we have given the name, we have given the description, we have given the environmental variable, and we have selected the default compute shape and the block volume and the logging configuration. Now let's come back to the pipeline steps. So let's click on add pipeline steps. So we are going to be using build by script in this case. We are creating the steps out of the OCI jobs. We can use this option. In this case, we are going to be using a Python code. So we are selecting build by script option. We will give the step name. So let's say step 1. Step description. So this is for data processing. It doesn't depend on anything since this is the first step. We'll select a step artifact here. Select file. So this is the zip file that we are using. And we have to give the entry point. So entry point is basically a py file that we want to begin the code execution with. So there's a py file within this zip file of the same name. So we are going to be providing that name. There is nothing else that we need to define right here. So we are going to click on save here. So the step 1 is created. Let's create a step 2. So once again, step 2A, because we'll be creating 3 steps for the training, step 2A, 2B and 2C, and they will be executing parallelly, and they will be training 3 different models. So let's say train linear regression model, LR model, depends on. So depends on step 1. Now we'll upload the step artifact once again. So which is LR in this case. So we'll upload this. Entry point, the py file with the same name. And save. So step 2B, step description, train random forest model, depends on step 1, because we are going to be executing the step 2B parallelly. RF LR RFZ here. Entry point, save. So depends on step 1, depends on step 1, build by script. Step 2C, train XGB model, depends on step 1 once again. Upload an artifact, step artifact, XGB.zip, save. Okay, entry point we didn't give. And now the final step. Step 3, step description, evaluate and deploy. Now in this case, the step 3 depends on all these steps, 2A, 2B, 2C. So when the step 2A is complete, when step 2B is complete, and when step 2C is complete, we are going to execute the step 3. So evaluate and deploy the entry point. save. So once again, we can check. Step 3 depends on step 2A, 2B, 2C, and that's pretty much. So we have defined all our steps. We also have defined all the pipeline parameters as well. So let's go ahead and create a pipeline. So let's see what has been created for us. So you can see that essentially all the steps that we had created here, the names have come here. Depends on column shows us. So step 1 doesn't depend on anything. Step 2A, 2B and 2C depends on step 1. Step 3 depends on step 2A, 2B and 2C. They are all of the script type, and we can see the step artifact here. So data proc, LR, linear regression, random forest, XGBoost, and then we have the evaluate and deploy here. So here is the pipeline that we had created earlier. We can see all the information related to it, including general information, infrastructure configuration, and logging configuration. We can see the default configuration that we had created, the environmental variable data location. Now we can begin a pipeline run by clicking start a pipeline run button over here. So we can give the name of the run. So we can say run 1 here, or anything else that you would like to have. We will not override any pipeline configuration over here. As far as the steps are concerned, actually, we will be editing the pipeline step configuration here. So we'll be adding 2 variables here, environment type. So we are providing an environment, conda environment of the service type here, and it's slug. Conda env slug. And rest of the things we are going to leave as it is. We are going to save this, and the same process we are going to repeat for step 2A, 2B and 2C. And step 3, I have completed the configuration for all these steps. We can quickly check for step 1, for step 2A, for step 2B, for step 2C, and finally for step 3. We also had set the logging configuration earlier. You can just quickly check it. So we have the pipeline log group already configured. So we are good to start a pipeline run. We will click the start button here. And as we can see here, the pipeline run has successfully started. And we can check the statuses here for the step 1 to step 3. The state right now is waiting. We can see the log group here. Time accepted, time started. We can also check the pipeline configuration once again. So we already have a data location here. So now there is a change in the state. It has gone from waiting to accepted, the step 1. If I click on the step 1, I get the pipeline step run information here. The status is accepted, type is custom script, time started, and we can check the runtime configuration also over here. So we see that the entry point is here, conda environment type and slug is also set here. We can see that the step number 1 has completed the execution. It has gone into the succeeded state. And the step 2A, 2B, and 2C, they also have changed the status. Step 2A is accepted, 2B and 2C is in progress, and the step 3 is still waiting because the steps 2A, 2B, and 2C they have yet to be completed. So we can see that all the pipeline steps have completed successfully. We can quickly check the log as well. The AUC scores for all the models that were trained that are also logged. So you can see that for linear regression, the AUC score was 0.85. For random forest, it was 0.81. For the XGB, it was 0.837. So the best model was the linear regression model with a AUC score of 0.85, and that is the model that was deployed. So let's go back to the data science project. So let's click the project details and let us check the models. So we can see that this was the model that was found to be best, and it is still active. And the same model was also deployed, so we can see the deployment for this model as well. So in this demonstration, we got to learn how to create a pipeline, how to run a pipeline, and how to automate an end-to-end machine learning workflow. I hope you find this useful. Thank you.
Hello and welcome to this lesson on auto scaling, a part of OCI data science course. When setting up a model deployment, it's crucial to make decisions about the appropriate compute shape and the number of instances which will provide a cost-efficient solution to our users. Predicting the best scale for deployment can be challenging because of external variables. Balancing the need for constant availability and best performance against cost efficiency is a common dilemma, especially when dealing with unpredictable workloads. And to solve this common issue in machine learning and data science application, we have introduced auto-scaling in OCI data science model deployment. Auto-scaling offers a solution by letting you define a range of number of instances, empowering the service to automatically scale up or down as demand fluctuates. This approach ensures efficient resource usage while accommodating increases in usage. You can set usage thresholds that trigger the scaling process, letting you control how quickly the deployment adapts to changes in demand. Moreover, you can extend auto-scaling capabilities to load balancers. By specifying a bandwidth range with minimum and maximum values, The load balancer adjusts automatically to varying traffic requests. This not only enhances performance but also contributes to effective cost management by dynamically responding to changing workload demands. Some key benefits of auto scaling for model deployment include dynamic resource adjustment. So auto scaling automatically increases or decreases the number of compute resources based on real-time demand. This ensures that the deployed model can handle varying loads efficiently. The second is cost efficiency. By adjusting resources dynamically, auto scaling ensures you only use and pay for the resources you need. This can result in cost savings compared to static deployments. The third one is enhanced availability. Paired with a load balancer, auto scaling ensures that if one instance fails, traffic can be rerouted to healthy instances, ensuring uninterrupted service. The fourth one is customizable triggers. Users can customize the auto scaling query using MQL expressions. The fifth one is load balancer compatibility. Auto scaling works hand in hand with load balancers, where load balancer bandwidth can be scaled automatically to support more traffic, ensuring best performance and reducing bottlenecks. And the sixth one is cooldown periods. After scaling actions, there can be a defined cooldown period during which the autoscaler does not take further actions. This prevents excessive scaling actions in a short time frame. So metric-based autoscaling is the supported method for autoscaling in a model deployment, wherein an autoscaling action is triggered when a performance metric meets or exceeds a defined threshold. At the moment, only one metric-based autoscaling policy can be added. Metric-based auto-scaling relies on performance metrics collected by the monitoring service and emitted by the model deployment resource such as CPU utilization. These metrics are aggregated into specific time periods and then averaged across all instances in the model deployment resource. When a set number of consecutive values meet the threshold, an auto-scaling event is triggered. A cooldown period between metric-based auto-scaling events lets the system stabilize at the updated level. The cooldown period starts when the model deployment reaches the active state. The service continues to evaluate performance metrics during the cooldown period. When the cooldown period ends, auto-scaling adjusts the model deployment size again if need be. In the predefined type, you can choose one of the two metrics, either CPU utilization or memory utilization, and specify thresholds for the scaling conditions. In a custom scaling metric type or expression, you have complete control over defining the scaling conditions in the form of MQL expressions and selecting any model deployment metric you want. You can create a model deployment with compute and load balancer auto-scaling configured. Consider using a custom scaling metric type for setting up auto-scaling with more advanced options and metrics on the model deployment. Ensure that you have added the necessary policy required for auto-scaling to work. You can create and run model deployments using the console, the OCI CLI, or the data science API. You can also enable auto-scaling for an existing model deployment or update any existing auto-scaling configuration. For model deployments in an active state, note that the modifications to the auto-scaling scaling policy fields must occur independently without simultaneous changes to other configurations. However, updates to fields such as display name, descriptions, tags, and other non-infrastructure related aspects are allowed. In contrast, when the model deployment is inactive, you have the flexibility to change all options simultaneously. Use the custom metric option to use any of the model deployment metrics emitted by the model deployment resource to create an MQL query, which can then be used to configure auto-scaling. This approach lets you create more sophisticated queries, such as joining several queries using AND and OR, using different aggregation functions, and incorporating an evaluation window of choice. By using this option, you gain greater control over the scaling conditions, enabling a more tailored and precise setup. So this is the policy allows service auto scaling to read metrics in tenancy where target.metrics.namespace equals OCI underscore data science underscore model deploy. So this policy has to be added to your tenancy. Metrics are automatically available for any data science model deployments that you create in OCI data science model deploy namespace. You don't need to enable monitoring on OCI resources to get these metrics. Data science model deployment metrics include dimensions such as resource ID, status code, status family, instance ID, result, and network type. And these are the different metrics. So again, as I said, you can use CPU utilization or memory utilization, or you can define your own custom metrics where you are free to choose any of these metrics.
First of all, let me congratulate you on reaching so far in the course. My name is Hemant Gahankari. I am a senior principal training lead at Oracle University. In this video, we will talk about a recently introduced feature of the OCI data science service, namely pipelines. So pipelines help us automate complete end-to-end machine learning workflows, including multiple steps, say for example, data extraction, data validation, data preparation, and so on. And these steps can be in sequence or they could be in parallel also. Pipelines is a very powerful feature in terms of automating your machine learning workflows. And I would definitely recommend you to go through the documentation and also explore using pipelines if you want to automate machine learning workflows. Thanks for watching.
Hi, in this module, we're going to be discussing related OCI services that are available to you. And specifically, we're going to be talking about Spark applications, data flow, and the integration with data science. I'm Jean-René Gauthier. I'm a product manager for the OCI data science service. So let's go over first an introduction to Oracle Cloud Infrastructure data flow. Data flow provides a scalable environment for developers and data scientists to run Apache Spark applications in batch execution at scale. Spark is a popular multi-language open source engine for executing big data workloads for data science and machine learning with Data flow, you can run applications within any Spark language, whether it's PySpark, SQL, Java, or Scala. You can leverage the Spark ecosystem of tools to perform a variety of data preparation tasks, including data aggregation and transformation, feature engineering, data joins, and data cleaning. The Spark distribution also come with the MLlib machine learning library, which offers a comprehensive set of algorithms and models that can be trained at scale on Spark data frame. Beyond MLlib, other machine learning libraries are also available in the Spark ecosystem for data scientists who can code in Python. A fully managed serverless service, Dataflow allows developers to focus on their applications and provide a runtime environment to execute them. There is no Spark cluster or infrastructure to provision. The execution is done in batch and is entirely on demand. It is driven by REST APIs, giving you easy integration with applications or workflows. It also has a rich user interface where you can create, edit, and run Spark jobs at any scale for machine learning training and batch jobs. Dataflow can read data from a variety of Spark-compatible data sources, as long as you include the connector in your application. However, it is really best suited to process data stored in object storage. Dataflow has four main components. The first one is a library, which is a central repository of Dataflow applications. Anyone can browse, search, and execute applications published to the library if they have the correct permission in the Dataflow system, of course. An application is an infinitely reusable Spark application template that consists of a Spark application, its dependencies, default parameters, and a default runtime resource specification. Once the developer creates a Dataflow application, anyone can use it without worrying about the complexities of deploying it, setting it up, or running it. Every time a Dataflow application is run, a run is created. The Dataflow run captures the application's output, logs, and statistics that are automatically securely stored. The output is safe so it can be viewed by anyone with the correct permissions using the UI, the REST API, the SDKs, or the CLIs. Spark generates Spark log files, which are useful for debugging and diagnostics. Each Dataflow run automatically stores log files in an object storage bucket. You can access them via UI or API via the SDK or the CLI, subject to the run authorization policies. So what are the Dataflow key capabilities? The flexibility and simplicity of Dataflow makes running Spark apps easy. You can, first of all, connect to Apache Spark data sources and launch a job in seconds. You can manage all Apache Spark application from a single platform. You can bring your own connectors to connect to object storage or other data sources. You can create reusable Apache Spark application in any Spark language. You can process data in the cloud or on-premise in your data center. You can execute any Spark application, perhaps in your case, PySpark and SQL, with no changes to the source code. Dataflow keeps your data secure through several privacy and policy measures. Clusters, virtual machines, and networks are all private, and your tenant's job run is in an isolated pool. No clusters are shared among users, so there's no conflicts of version between packages and libraries. Logs are securely captured and put in object storage. Data is encrypted at rest and in motion, and Dataflow is also integrated with OCI identity and access management for authentication and authorization. The Spark applications run on behalf of the person who launches them and inherits their privileges. So you don't need to use credentials to access any IAM-capable system from your Dataflow job. Why does Dataflow, or why would you use a Spark, and how do these tools really benefit AI and ML workloads? So Spark is one of the most popular engines for scalable computing. It is used by most Fortune 500 companies and is often leveraged for AI and ML workloads because it can process data effectively at scale. Spark and Dataflow gives you a highly scalable engine to do ETL, so extract, transform, and load work, data processing and feature engineering, and also model training. It's an alternative to data science jobs, for example, for data wrangling or model training tasks that are relying on industry standards. Spark lets you run SQL queries on your structured data and manipulate familiar data frame objects. And then the Spark distribution also comes with the MLlib machine learning library. And MLlib offers a comprehensive set of algorithms and models that can be trained on Spark data frames. This is how Spark applications are configured. First, Spark resources are selected when an application is created in Dataflow. You must select the driver and the executor shape and the number of executors for each resource. They are then spun up and down each time the application is run. Spark context is the entry point for any Spark functionality, and the Spark driver is the central coordinator that executes the code. It communicates with a cluster manager, which launches the Spark application, and multiple distributed worker nodes. Each node has at least one executor, which is responsible for running the tasks. Executors register themselves with the driver and provide with their information. This working combination of driver and workers is known as the Spark application. When choosing the right number of executors, there are a few things to consider. The more data you have and the less time you allocate to process it, the more OCPUs you will need. For example, if you want to process 500 gigabytes of data in 10 hours, you will need around 5 executor OCPUs. Dataflow also integrates with the Oracle Accelerated Data Science Python library. You can submit a Spark application or run your Dataflow jobs using ADS, which is pre-installed in notebook sessions. Now that you're familiar with Dataflow, let's look at how to use it and data science to create and manage Spark applications. What are the prerequisites here? Using Dataflow with data science notebooks assume that the prerequisites for using data science have been met. This includes having a user account with proper permissions in a data science project and a notebook. Once those have been set up, you can prepare to use Dataflow. What you will need is an object storage bucket to hold data flow logs and a Dataflow warehouse. You'll need a Spark application in Java, Spark SQL, or a PySpark uploaded to object storage. You will need data for processing that's loaded in object storage. And then you'll need the policies granting proper permissions to storage buckets and other resources. So once the data flow is set up in your tenancy, you should be able to launch a data science notebook session, develop PySpark applications, and submit data flow runs. We recommend using notebook session as an interactive development environment, or IDE, for PySpark applications. In the next lesson, you'll see a demo of this process. First, let's go over a few best practices. There are a few best practices when you develop Spark application from a notebook session environment. First of all, use a sample of your data. Do not load an entire data set from object storage in your notebook session. Use the notebook to develop your PySpark Python script iteratively. Break down your code into cells, convert Spark data frames to Panda data frames, and visualize the results, perhaps with Matplotlib. You want to remove the cells that you do not need and convert the notebook into a Python script using this particular terminal command. And just replace, my notebook.ipynb with the name of your notebook, and this command will create a new Python script file for you. Test your script locally using the Spark submit command before you submit it to Dataflow. Open a terminal window and activate your PySpark environment. Then you can execute the command, the Spark submit command of your Python script. Before you create an application with Dataflow, make the relevant changes to your script. If you use only a sample of your data, for example, you could change that and point to all the data in your bucket. You should also remove all references to third-party Python libraries. For example, if you use pandas or matplotlib or scikit-learn that are not part of the Spark distribution, you can add these libraries to the Dataflow runtime environment, but we're not going to cover this topic in this lesson. I would advise that you consult the Dataflow service documentation. ADS is a comprehensive SDK to help you create Dataflow applications and run. We strongly recommend that you read the ADS Dataflow documentation on docs.oracle.com. There are other common operations that you can perform with ADS, and those include loading an existing Dataflow applications in your notebook session, listing existing Dataflow applications, fetching logs, editing and synchronizing PySpark script with Dataflow, defining use arguments and parameters in Dataflow applications and run, and adding third-party libraries to the Dataflow environment. To wrap up, we've covered in this lesson a brief overview of the Dataflow service. We've gone over the interaction between Dataflow and data science, and we give you a few best practices on how to develop your PySpark application inside of the data science notebook session. Thank you so much.
In this short lesson, we'll cover Oracle Open Data. I'm Wes Pritchard, Senior Principal Product Manager for Oracle Data Science and AI Services. Oracle Open Data is a service from Oracle for Research that makes large data sets available to researchers around the world. It curates information like spatial images, protein sequences, and annotated text files from the world's leading scientific data sources. Oracle Open Data is a dataset repository made for the people that create, use, and manipulate datasets. Datasets are freely available with no need for login nor payment. Datasets include geospatial data from satellite systems such as GOES, MODIS, and Landsat. Also available are various life sciences datasets, including chemical compounds, protein sequences, CT images, and genomic data. Oracle Open Data is also relevant for data scientists because the repository includes data for AI and ML, such as various types of images, and book corpuses in both text and audio format. Oracle Open Data offers several benefits, including trusted, accessible data. Data is curated, managed, and ready to use. Datasets come from trusted institutions like NASA, DeepMind, and Stanford. With Open Data Platform, it's easy to navigate, search, and download files. You can access the latest datasets with the frequently updated repository. And each dataset consists of code and tooling usage examples for consumption and reproducibility. Oracle Open Data can be accessed online at opendata.oraclecloud.com. Just click the Explore Repository button to navigate to the data collection. Look to Oracle Open Data as a resource for open data in a variety of domains from trusted sources.
Hello, my name is Praveen Patil, and I am a Principal Product Manager within Data Science and AI Services Group. This lesson covers what is data labeling and gives an overview of Oracle Cloud Infrastructure Data Labeling Service. What is data labeling? Data labeling is the process of identifying properties for image or text data and annotating them with these properties or labels. The data can then be analyzed or used according to the labels given. For example, 100 labeled images of various tigers or signatures can teach an AI system how to locate additional tigers or signatures in unlabeled photos or documents. Many machine learning or ML techniques require labeled data before they can be used to train machines to complete a task autonomously. Data labeling is therefore an integral part of an AI ML project. Datasets are core resource of data labeling service. Datasets are made up of data records and their associated labels, such as tigers or signature in this case. Data record is nothing but individual images, text files, or documents. These datasets are accessible and interoperable across other data and AI services to support supervised machine learning. For example, OCI vision services can be used to create specialized model to gain insights, but only if labeled data is first available for training the model. Data labeling lets you quickly start labeling raw data sets with a minimal number of configuration steps. Load your data, label them, and use labeled data sets across OCI AI services and data science. Who uses data labeling? You have two personas, either data scientists or developers and engineers. Data scientists who need to build labeled data sets, they assemble the data set and data records such as images or text. Choose pre-built rich UIs for labeling and export the labeled dataset. These exports then serve as input to build and train deep learning models within OCI data science service. Developers and engineers also use data labeling service to build their own labeled dataset, which is then used to further fine-tune AI services models, such as image recognition model, which is then deployed. They assemble the dataset, label it, and provide it to AI services. Various industries have a wide range of uses for data labeling. As you can see, retail, e-commerce, manufacturing, insurance, government, healthcare, media and entertainment, to name a few. In media and entertainment, social media and customer feedback is often scrubbed to flag inappropriate image and text content and to note the most common words used in order to gauge customer sentiments. In retail and e-commerce, online shops analyze customer behavior data in order to provide relevant recommendations for future purchases. In healthcare, hospitals analyze large sets of medical imaging in order to more accurately identify anomalies in future scans. This is a high-level view of an AI/ML lifecycle. Data labeling occurs early in the process because you cannot analyze or utilize data that hasn't been labeled to build customized models, especially using semi-structured or unstructured data. This also means that poor data labeling can impair the rest of the model creation and deployment process. Poorly labeled dataset leads to distorted, inaccurate, or incomplete results. MLOps is an iterative process. It all starts with having good quality data to build your initial model. Model training is also an iterative process that might involve labeling new images or text or editing existing labeled data if the desired accuracy or precision isn't met. For example, an initial set of labeled data might have underrepresented label classes without even enough example. This leads to low accuracy and precision in custom model training results. An extra set of images or text will need to be labeled to teach the model more about these classes. The custom trained model will then more accurately detect that label classes from new images or text. Even after your model has been trained, if enough drift is later detected, you might want to label new images or text to retrain and redeploy the model. The current capability of data labeling service focuses on simple and fast use cases. Developers, data scientists, or data labelers can use interactive user interfaces or APIs to upload images, text, and documents and quickly annotate them. They can then export and use these datasets across many of Oracle's AI and data science services for a seamless model building experience.